Alright, now we'll take a look at improper integrals with infinite discontinuities. Now, an infinite discontinuity is basically a vertical asymptote. So we're basically looking at integrals that involve vertical asymptotes on the interval on which we hope to integrate. So for instance, if f is continuous on this half-open interval, notice it doesn't say that the function is continuous at b. b is excluded from this interval. So we have a function that's continuous on a half-open interval and has an infinite discontinuity at b. Well, the reason why it's not continuous at b is because there's a vertical asymptote there, an infinite discontinuity at b. Then the integral from a to b of f of x dx is equal to the limit as c approaches b from the left. So the interval from a to b is everything to the left of b and to the right of a. Everything that's both to the left of b and to the right of a. So that's why we're approaching b from the left, because this function is continuous on the interval to the left of b. So we're taking the limit as c approaches b from the left of this integral from a to c f of x dx. Alright, so basically we're integrating all the way up to the vertical asymptote b. Now for number 2, f is continuous on the half-open interval that doesn't include a but includes b. It doesn't include a because there's an infinite discontinuity or a vertical asymptote at a. So this is the case where the vertical asymptote is on the left side of your interval. So here's the vertical asymptote being on the right side or at the end of your interval. Here's the case where the vertical asymptote is on the left side or the beginning of your interval. Then here's the limit. We're doing the limit as c approaches a from the right. Because this vertical asymptote is on the left of the interval, you have to approach a from the right of that integral. And here's the case, number 3, when the vertical asymptote is in the middle of the interval. So the function is continuous on the closed interval from a to b except for some point c that's in the open interval from a to b. So basically, in the middle of your interval from a to b, you have some point c where x equals c is a vertical asymptote, or a infinite discontinuity. Then what you do is you split the interval up into the interval from a to c and the interval from c to b, and then you can use these two definitions to find those two integrals. So number 3 combines number 1 and 2 when the vertical asymptote is in the middle of the integral, or in the middle of the interval, not integral. So let's put this to use to do a problem. Alright, so the one that I want to look at is the integral from 0 to 4 of 1 over the square root of x dx. What I want you to notice is that x equals 0 is a vertical asymptote. So the graph never actually gets to the value where x is equal to 0. It just keeps approaching that vertical line, x equals 0, which is the y-axis. It just keeps approaching the y-axis, but it never actually gets to the y-axis. So because of the fact that this integral has a lower limit that is that vertical asymptote, we have something that is not a proper integral. Because for this to be a proper integral, this function would have to be continuous on the entire interval from 0 to 4, and we found out that this function is only continuous on the interval from 0 to 4 excluding 0. So because of that, this is an improper integral, because it should be continuous on the entire closed interval, but it's only continuous on this half-open interval. So this is what we have to do. We have to use the first definition we had, and actually, in this case, the vertical asymptote is actually on the left side of this interval, so we're actually going to use that second definition. The second definition said that this is equal to the limit as a as actually the limit as c, I think is what we use. The value that we used was, the letter that we used was c. Yeah, the limit as c approaches a, which is 0 in this case, from the right. So it's the limit as c approaches 0 from the right. I know I'm coming from the right because this vertical asymptote is on the left of the interval from 0 to 4. So I know I'm coming from the right because these numbers are on the right of 0. So it's the limit as c approaches 0 from the right of the integral from c to 4 of, I'm going to rearrange this integral now and write it as x to the negative 1/2 dx. Because I know I'm going to use the power rule to do the integration. So this is what that definition I just gave said. It said if the function is not continuous or has an infinite discontinuity at one of the endpoints of your interval, then you have to actually take the limit as c approaches that endpoint, and that's the way we're going to calculate the integral. So let's go ahead and integrate. This is equal to the limit as c approaches 0 from the right, and then we're going to do this integral. Well, it's going to be adding 1/2 to negative 1/2. Adding 1 to negative 1/2 gives us positive 1/2. So this is x to the positive 1/2. And dividing by positive 1/2 is the same as multiplying by 2. And we're taking this from c to 4. So this is equal to, let's see, first we're going to plug in 4. That's going to give us the limit as c approaches 0 from the right of 2 times, this is the square root of 4 minus 2 times the square root of c. Well, 2 times the square root of 4, that's 2 times 2, which is 4. So this is the limit as c approaches 0 from the right of 4 minus 2 square roots of c. And as you approach 0 from the right in the square root function, the square root function tends to 0. So this term will tend to 0, and this limit will be 4 minus 2 times the square root of 0, which is just 4. So the limit converges, or the integral converges. The integral converges, and it converges to the number 4.